Hello everyone, my name is Nengru. I'm now working as a postdoctoral fellow at the Laser Research Institute of Hunan University. Today we are going to discuss an interesting research topic, that is, understanding the ball-bonding effect in ultra-short pulse laser drilling of CFRP laminates. The first step, we're going to talk about the research background. Carbon fiber reinforced plastic CFRP laminates have gained increasing interest from aviation, aerospace, and rail-related industries due to their excellent material properties. The corrections between CFRP components are usually bonded or regulated by drilling holes. In this case, the drilling quality can significantly affect the collection strength between CFRP components. However, for conventional drilling method, drilling reduced defects such as delaminations, burrs, and cracks can be frequently generated. Consequently, developing the unconventional drilling method is of great significance to improve the hole processing quality. Ultra-short pulse laser drilling of CFRP laminates provides an excellent alternative for the drilling CFRP due to tool wear-free and high machining flexibility. The common drilling process by ultra-short pulse laser drilling could be classified to single-pulse drilling, percussion drilling, trepanning drilling, helical drilling. These drilling processes are mainly used for the drilling of thin laminates with small diameters, because the laser beam moves around in repeated cycles. Recently, a coaxial trepanning drilling process which combines the trepan drilling process and the parallel path cutting process is applied for the drilling of thin and thick CFRP laminates, as shown in Figure 1. The laser beam moves with a scan speed in a circular trace ranging from R-max to R-min. The design internal distance is d, which is less than the diameter of the focal slit. The moving laser beam is controlled by 3D scanner galvanometer. The material operation starts at the initial plane of the designed drilling radius R-max. Finally, the laser beam arrives at the last position of the designed radius R-min. After finishing one drilling pass, the laser focus shifts to the retraced focus plane. The total drilling depth of the CFRP laminate can be obtained by repeating the above process. The coaxial trepan drilling process shows the advantages in drilling of CFRP laminates. However, the generation of hole table, heat effect zone, and related drilling depths during such later drilling process has become the main limitations for its further applications. Hence, this work is to understand the formation mechanism of hole table, HH, as well as the drilling efficiency related to the drilling depths. Experimental materials and setup to verify the formation mechanism of hole table. Two different cycles of CFRP laminates are used. As shown in Figure 2, a 100-watt picocycle laser is used. The scan speed of the laser beam is controlled by 3D scanner system. The processing conditions are shown in Table 2. The experimental result. Ball-bonding effect. Figure 4 shows the typical cross-section morphologies of CFRP laminates with a thickness of 0.7 mm. From the figure, it can be found the whole cross-section table is quite small close to the entrance of the borehole, whereas the whole table is quite large close to the hole exit. The whole table shows a sudden increase close to the hole exit, which just like the bottom of a bowl, and is named as ball-bonding effect. The whole table of arbitrary point at the cross-section can be calculated by the table equation 2. Figure 5 presents the typical whole tables of the two thicknesses, calculated by equation 2. As marked by the purple line in Figure 5b, for the drilling of 9.7 mm laminate. The whole table slowly increased from 3 to 5 degrees in the drilling depth range of 1 to 3 mm. However, for the drilling depth range of 7 to 9.7 mm, the whole table sharply increased from 13 to 36.5 degrees. The marked whole table appeared at the whole exit. The whole table has a sudden increase at the drilling depth range about 6.5 to 7.5 mm, decreasing thickness of CFRP laminate to 4.4 mm. A similar trend can be observed as shown in Figure 5a. Here we developed a theoretical model for the formation of a whole table and divided it into 3 stages: information stage of table, stage 1, table accumulation stage, stage 2, and bubble formation stage, stage 3. For stage 1, as shown in Figure 6a, proposed later, for example, beam 1 at the almost circular path irradiated on the initial plane of the CFRP laminate. Since most of the laser beam produced by conventional post-laser is Gaussian beam, the intensity of the laser beam is higher in the center than that of the region away from the center. In this case, the energy distribution of arbitrary point within the focus spot IXY can be expressed as equation 3. From equation 3, it can be found that for the drilling of CFRP caused by the outmost post laser, the cutting curve of the material will produce the initial table related to the energy distribution of the laser beam. Subsequently, the laser beam, for example, from beam 2 to beam N shifts to the subsequent circular path until it reaches our mean position. For this context, the large cutting curve can be formed on the processing surface. For stage 2, the post-laser beam continues to irradiate the deeper material. With the increase of drilling depth h, the laser focus needs to reach to the focal plane. For the laser beam along the initial looper path, the laser energy absorption by deeper material is sharply reduced due to the shed of the sharper slope surface. For a sudden retrace focal depth h, the radius of the expanding laser beam RH at the upper slope surface of a depth HI can be expressed as equation 4. The area of a focused spot can be expressed as equation 5. The laser average fluence for a single pulse can be denoted as equation 6. On the other hand, since the upper surface is sloping, the projected area of the incident laser will also expand, which further leads to a decrease of the laser fluence. Assuming that the laser beam is incident at an arbitrary point on the upper slope surface with the depth HI, the focus spot will for a projected area as beta I associated with the whole table beta I. Obviously, the projective area as beta I will be larger than the focus spot area SH. Here, assuming that the vertex of conical surface is the origin of Cartesian coordinates, the projection of focus is in the negative direction of the x-axis. The coordinates of an aperture point xyz with the projected area can be expressed as equation 7. The integral of the projected area as beta I can be expressed as equation 8. From equations 7 to 8, projected area as beta I can be extracted as equation 9. From equation 7 to 9, the final laser average fluence FHI can be calculated as equation 10. From equation 10, it can be found that the decrease of the final laser average fluence FHI are attributed to two aspects. One, that the incident laser being shaded by the upper slope surface led to the expansion of the focused area SH. In addition, the variation of the whole table beta I could lead to the expansion of the projected S beta I. Herein, assuming that the whole table beta I is 19 degrees, the laser average fluence as a function of different depths of HI on the upper slope surface for a retraced focal depth 9.7 mm are shown in figure 7a. It can be found that initially the average F-link can only be obtained at the upper slope per surface depth of HI equals to 9.7 mm. For the upper slope surface depth of 0 mm corresponding to the start plane, the decreased laser average fluence FHI is only 1.4% that of the initial average fluence at a low power of 75 watt. For the stage 3, as shown in figure 6c, the post laser being continued to irradiate the deeper material with the accumulation of whole table. The great majority of the incident laser will be shaded by the upper slope surface. The cutting curve will be laterally, and only a small number of incident laser beams can reach the retrace focus. For this context, if the average fluence FHI is larger than the aberration threshold of CFRP material, the shaded laser beam will repress the upper slope surface, namely as secondary processing. Hence, the whole table will decrease. Notably, the laser draining efficiency will be quite low at this stage. To verify the theoretical analysis, further laser draining experiments were conducted. From figure 8a, it can be found that when the Lambert draining path was 20, the shape of whole table curve was steep. This is consistent with the Gaussian distribution characteristic of the laser beam energy. For this context, the maximum whole table at the bottom of the cutting curve can be small. When the number of draining passes increase 100, the draining depth increased about 4 mm. The cutting curve became narrow. In further increasing the draining passes to 200, the draining depth increased to about 6.8 mm, and the maximum whole table increased to 42 degrees. Meanwhile, the cutting curve became quite narrow. Subsequently, when the number of draining passes increased to 374, the borehole was obtained and the shape of the whole table curve became deep again. Finally, the shape of ball bottom is produced. Figure 12 shows the typical image of HIG for different thick laminates caused by laser draining. From the figure, it can be found that the HIG of cross section was quite small, except for the last few plies close to the hole exit. The HIG size increased gradually for the last few plies until reaching the master value, hundreds of microns. It indicates that the HIG size would sharply increase due to the large hole table close to the hole exit. The differences of draining efficiency caused by different laser powers are shown in figure 15, as marked by the red line in figure 15a. For the laser draining of 14.4 mm, the draining efficiency presents 3 stages corresponding to the 3 stages of the ball bottom formation respectively. When the draining depth was 2 millimeter. The total drilling time was about 4.9 minutes, which shows a rapid removal of material at the stage 1. Then, when the drilling depth was 4 millimeter, the total drilling time was about 30.1 minutes, which show a stable removal of materials at stage 2. The drilling efficiency decreased by 40.2% compared with that of stage 1. When the drilling depth was 4.4 millimeter, the total drilling time rapidly increased to 80.9 minutes, and the drilling efficiency decreased by 83.1% compared with that of stage 1. Notably, increasing the laser power to 95 watt could greatly improve the laser processing efficiency by 174% for the stage 3. It can be found for the drilling efficiency presented similar trend compared to that of drilling 9.7 millimeter laminates, as shown in Figure 15b. In general, the post-laser drilling efficiency for CFRP laminates is still very low compared with that of mechanical drilling. Further investigations could focus on the development of new laser drilling strategies, as well as the laser drilling with higher power to improve the laser efficiency. The conclusions. In summary, this paper have demonstrated a ball-bottom effect of whole table for the first time. The formation mechanisms of the ball-bottom effect was demonstrated. The expanding of focused spot area and projectile area depends on the upper surface depth and the variation of the whole table respectively, which can sharply decrease the laser average fluence. The formation of HAG is constant at the last few plies close to the whole exit due to the effect of secondary processing. Compared with stage 1, the drilling efficiency of stage 2 and stage 3 could decrease by 14.2% and 83.1% respectively, increasing the thickness of CFRP laminates. The drilling efficiency shows little difference at stage 1 and 2, but sharply decrease at stage 3. Okay, that's all. Thank you so much.